Okay, so let's get started. Thank you so much for joining. This is Exploratory online seminar number 85. This time, I like to introduce chi-square test. The chi-square test is about if there is a relationship between the two categorical variables. So it's part of the hypothesis series that I started it recently. So I think we have done that hypothesis test, kind of introduction to it. And then we have done a t-test, and this is the chi-square test. Let me introduce myself. My name is Kan Nishida, CEO at Exploratory. We started Exploratory 2016 to democratize data science. Since then, we built Exploratory as a product to make it easy to access various data science methods, and then a way to analyze your data. And also we provide this type of seminar and the training to share our knowledge and skills to democratize data science. Our vision is that data-informed decision-making is essential for making the world better. So I think what we can contribute by democratizing data science, by building the product, but also by sharing the knowledge. When we say the data science, we think in this kind of workflow. You usually start with questions and you want to answer with the data. So you have to access the data, and then you got to prepare and clean and transform the data. That way you can visualize or analyze. And you go back and forth in these steps, and then eventually, if you have found useful insights to be able to answer your questions, then sometimes you work with other folks, so you want to communicate what you have found with others. So that last communication is also the important piece of the data science workflow. The Exploratory provides these 5 things through the modern and simple UI. Okay, that's enough for the Exploratory and myself. Let's get started. So Exploratory online seminar number 85, chi-square test. This is a part of the hypothesis test series. This is actually the number 3 of that series. This time, sometimes you have the 2 categorical variables, and you want to find out the relationship between them is significant or not. I mean, the simple word is if there's a relationship between those 2 or not. And that's where this chi-square test comes in. This chi-square test is very useful. This is not just a statistical textbook kind of thing. This is actually one of the hypothesis tests that I think the most often or most commonly used in many of the tech companies, let's say Facebook or Uber or Airbnb and so on, because typically they do is running thousands of A/B tests every day. And then in order to evaluate whatever they do, they say A is better than B, they often use this chi-square test or something similar to it. Okay, so before you actually continue to watch this seminar, I strongly encourage you to watch what we have done in the past called Introduction to Hypothesis Testing. This is where I kind of made a groundwork for sort of a thinking framework, how you can actually think of this sort of hypothesis testing. Some of the kind of unfamiliar words and concepts comes in with this hypothesis testing. So I explained those, and also not just explain those terms, I explain sort of a background or a kind of how you can think as a framework. So I strongly encourage. But in this particular seminar, though, I'm going to just briefly touch at the very beginning. So to refresh yourself, or if you haven't watched other video, you can kind of start with it. Okay. So you can access to this past recording from our website, going to the Learn, exploratory.io. And then from the Learn, there's a training and seminar menu. And then you can get to find the past seminar. It's called Introduction to Hypothesis Testing. So in that video, in the seminar, I taught at the end, I said, hey, there's a bunch of hypothesis testing types. And then I listed these, and obviously, like these are the only, I mean, these are not the all hypothesis testing types. There are a bunch of others as well. But I think these are most commonly used. And then left-hand side is like a numericals. There are different variations to it. Today, we want to cover the categorical variables with chi-square test. Okay, so just to make sure, like what categorical I'm talking about, right? So it's categorical. It's basically like when you look at the data, which is the characters, not instead of numbers. That's categorical. Okay, so for example, when you have the data like attrition, let me just go back to go to the exploratory here. I have the employee data. Okay, and then like so each row is employee. And then like these columns, like 30 columns are about the employee's attribute information, such as how, age and income and which department they work in and that kind of stuff. When you see, for example, this is number, these are numerical variable. If you see the characters, there's a character, it's data type is a character, that's a categorical variables. That's a very, very simple way to categorize them as a categorical or numerical. Sometimes it doesn't, work that way. Even like numerical, it can be considered as a categorical, but I don't want to go into that kind of definition side of things. So this is a very simple way is this, when you see the character data types, often that's a categorical. I mean, most of the time that's a categorical. So here we have the attrition column, which indicates if a given employee has left the company or not. If it's true, it has left. If it's false, still with the company. And there's another column or variable here. It says overtime. That says yes or no. That means this person or this employee has worked overtime. I don't know, maybe like, let's say like last 30 days or something. Okay. And if it's no, this person hasn't worked overtime over the last 30 days or whatever the period. Okay. So I like to know if there is any relationship between these two categorical variables. Meaning, let's say the people who often work overtime tend to leave the company more than the people who doesn't work overtime. Okay, and if that's the case, maybe like that can give me some kind of insight. Hey, you know what? Like maybe like let's stop doing that. Working overtime thing. We got to be careful because we don't want to lose more employees. That kind of stuff. Okay, so we want to know the relationship, if there's any relationship between these two variables. Okay, that's where the chi-square test comes in. So chi-square test, this is a kind of brief summary of the chi-square test. And then after this, I'm going to go into more details and how this works. So chi-square test is to test if a given pair of the two categorical variables, such as attrition and overtime, are independent or not. Independent meaning they're not related. Okay, they're not depending on each other. It's independent. So that means there's no relationship. So another way to put it, we can evaluate if the relationship between these two categorical variables is significant or something that is worth our attention. Okay, so significant meaning like we should pay more attention. We should assume there's some relationship. May not be, but we should at least pay attention to it, right? And opposed to that, there's sort of like, there might be some kind of thing, but it's actually a marginal difference. Then maybe like, it's a waste of the time to spend more time investigating it or even pay attention to it. Okay, so we want to decide, should we pay more attention or should we move on? Okay, so that's the kind of decision making that we want to do by using chi-square test. Okay, so today, like I'm going to use this example, like attrition and overtime, these two categorical variables, are they related to each other or are they depending on each other? Or is there any relationship between these two? So I created a chart, left-hand side, the people who work overtime, right-hand side, people don't work overtime. So overtime or no overtime. And the yes or no, meaning the people who have left the company or not. Okay, so that's the attrition. So when you see this blue, means the people who have left. and the orange mean people who haven't left. And by just looking at this, and then, okay, looks like the same amount and same number of the people who have left, and then more people who haven't left on the, not overtime. So it seems like the overtime make employee tend to quit more than not overtime folks, but it's better to make it ratio, right? Make both of them 100%, and then what's the percentage of those have left or not left? And in that way, we can it's make it easier to compare, sort of like kind of apple and apple, because now the people are different between overtime and not overtime in general, in total, regardless of the attrition or overtime. So we want to make it it's a sort of same scale, which is in this case 100%, and then we compare by the ratio. And by just looking at this, obviously, well, I don't know, to me it's obviously left-hand side, the people who have who work overtime have more people that who left the company, okay, who left this organization. So that says maybe, okay, maybe like something to do with overtime or no overtime. Okay, so we are interested in like what type of people leave in the company. And I would say, hey, you know what, the people who work overtime has more chance to leave the company, right? But here's the question. The difference is this much. I don't know, this is like a 10%. 10% difference, to me, is like, yeah, that's actually a good, difference, a good amount of the difference. But is that significant or marginal? Because if it's significant, we got to do something about it, or at least we should investigate more. If it's marginal difference, then we should move on, or we shouldn't just spending more time. We have some other things. We are busy, right? So we have some other things to do. So I want to make decisions that if this is significant, that we should do something about it, or if this is marginal, that we should move on. Okay, so that's the sort of the premise. And then let's start looking into like what the whole chi-square test is. But before getting into the chi-square test, this is a hypothesis testing. So I like to go over the thinking framework for the hypothesis testing first, then go into the detail of a chi-square test. So when you think about a hypothesis testing, it's always helpful to think of this way. Like you have the two way of thinking, right? One is a deduction and the other one is induction. Deduction is starts from the assumption, or can be hypothesis too, but that's something that it's universally truth. We can assume that is true by sort of like anybody's eyes. And if start from that, then you use the logic to conclude that, hey, this can be whatever the things are happening, and this is because based on the assumption, I can explain this way. So like explain the real world by using the logic based on the assumption. That's the deduction. Right-hand side induction is that you don't start from something for sure, something like universal truth. Instead, you start from the real world. You observe first. And then based on the observation, you use the probability and then estimate the theory that can be applied in a kind of a generic world, or sort of a generalized truth. Right-hand side at the top, the theory can be wrong, nobody knows. Unlike the deduction, the assumption at the left-hand side top. Right, so right-hand side top is like nobody knows, but we assume, we estimate based on what we see in the real world. So these are two different approaches. From like left-hand side, you can say sort of like a top-down. Right-hand side is kind of like a bottom-up. Okay, so having said that, then the next thing important to know is like scientific method. Scientific methods probably shared by many, but I think that I like this chart because this is by Richard Feynman. You can Google, or you can go to YouTube to see his video, like I think 10, 15 minutes, he summarized what the scientific method is. It's very simple as everything else he explained. So start with guess. Basically, this is to define a hypothesis about your question, about your interest. Then you predict, meaning like you compute the outcome given the guess is correct. what kind of world is you're going to see if the assumption is correct, right? And then you test it in the real world, then see if that what you expected, what you predicted is really happening, or you really see in the real world or no. Okay, so in a typical scientific method, it's kind of like this. Basically, the same thing. The hypothesis, predict, test. That's the Richard Feynman's definition of the scientific method. But usually you start with a question, then you define a hypothesis, and then you define what you expect if the hypothesis is correct. Then you test in the real world. This is where you basically do some quote unquote experiment, right? And then you compare that what you see in the real world against what you have predicted based on the assumption that your hypothesis is correct. And then you study, see like if it's consistent or not consistent. If it's consistent, meaning what you tested and what you predicted are consistent, meaning matching, then you accept the hypothesis. Then eventually like you build a theory. But if it's not consistent, then you reject the hypothesis. According to Richard Feynman, if we disagrees with it, it's wrong. But this scientific method actually contains that deduction and induction that I was talking about. Basically, the deduction is like you assume the hypothesis is correct. So like this is sort of like a starting point. And then you imagine, or like you don't have to imagine, sorry. I mean, like you can imagine too. But most of the time you sort of like compute, what you calculate what is going to happen if the assumption is correct. That part is a deduction. And then going to induction is a real world, right? Like you want to experiment, experience or you observe, and then you sort of like build up that theory from there. So, but what you're actually doing is actually testing in the real world and see your hypothesis correct or wrong. And then according to George Box, who's a great statistician from UK, he was talking about this iterative learning process. Basically, the way we obtain the new knowledge is we go through this sort of like a deduction, induction. Okay, so this is, it's not like one way is better than the other. Like we actually use these two to get closer to the truth or obtain a new knowledge. So use the where's my car example. I can't find the car. So immediately I thought my car was stolen. If this is the hypothesis, then like what the world should be like. And then like I basically use the logic to say, hey, my car should not be in this parking lot. Okay. And then what I should do is to test it in the real world. And I'm going to just dig in, like I'm going to look around every corner of the parking lot. I couldn't find it. And that's what's happening in the real world. So, I'm sorry. I found it. I found the car, just a different spot. So that means that my hypothesis, my like sort of prediction left-hand side is not consistent with what I see, what I observe. So the world of theory, left-hand side, the world of reality is not consistent. Therefore, I can reject the hypothesis. That is the starting point, and that is not, that is the whole reason I ended up like a concluding on the left-hand side. That's not working. So therefore, I can reject the hypothesis, and then my conclusion would be my car was not stolen. We can see like opposite side too. Hey, you know what? I couldn't, right-hand side bottom, I couldn't find a car anywhere in the parking lot. That means the left-hand side, world of theory, and the right-hand side, world of reality is matching, consistent. Therefore, I can accept the hypothesis, and then I can move on. I can go on with like, hey, you know what? Like my car was stolen, right? My car was stolen, but there was a typo there. Anyway, so that's the thinking framework for the hypothesis testing. So now let's look into the particular case for the chi-square test. So we want to see like if there's a relationship between these over time and attrition categorical variables. So bring that framework. So that let's start with hypothesis. But when you do the hypothesis testing, you have to start with the not like whatever the hypothesis. In this case, particularly, specifically, it has to be falsifiable hypothesis. And falsifiable hypotheses tend to be like nothing or zero. Then we can sort of like start from there instead of like there's a relationship. Instead of starting like instead of stating there's a relationship, we want to go with there's no relationship. Then you can see the signal that is coming out from zero, like right, and it's easy to say like, hey, there is a signal coming out. I mean, something's not zero. So we have some sort of like a criteria there. But anyway, so we start with there is no relationship between attrition and overtime. And this falsifiable hypothesis tend to be like no relationship or no difference type of thing. Is we call it null hypothesis in hypothesis testing. Okay. And then if that is correct, or if we accept that hypothesis, or in this case, particular case, null hypothesis, then what the world is going to look like, then there is no difference in attrition rate between overtime people and non-overtime people. Okay, so that is something we expect. Now the left-hand side is done, then go to the right-hand side, induction side. Then we have to test in the real world. Left-hand side is just theory, so we want to test that if that's happening in the real world or not. And then we look at the data, and the same chart we saw before, and hey, there's a difference here. People who work overtime has more percentage of the people who left the company. So therefore, we can conclude that somehow there's a relationship between these two. But the problem here is this difference is significant or not, because in this world we live, there's always a variance. Okay, there's not like a static or there's a fix or something. There's always some kind of variation, even there's no relationship. I'm sorry, there's no relationship. So we want to see like if there's this, let's say like 1% difference is big difference. If should we care? If it's 5%, is that big difference? Should we care? 10% difference, should we care or should we just move on? So like how we can decide, right? So that's where this how we define the significant difference here. So let's focus on what the difference here is. Like, well, what should we expect if there is no relationship? Okay. So if there is no relationship between attrition and it says gender, but it's not gender. Sorry about that. This is supposed to be overtime. Okay. Overtime. Then the ratio of attrition for the overtime and the ratio for no overtime should be equal. And the chart look like this. Both of them is like, hey, 20%, 20%. When you look at the chart like this, then you're like, okay, like, if you work overtime or not, doesn't really matter if you might quit or not quit, right? So having said that, left-hand side is what we got from this data. Right-hand side, theoretically, we expect if there's no relationship, we should see the chart like this. That's the right-hand side. So right-hand side is sort of like a kind of theorized world or like deduction world. And the left-hand side is actual data, the one we have in the real world, okay? So when we have these two, then we want to know, we already know there's a difference in the actual data. The percentage of the people who left overtime is bigger than the percentage of the people who have left not overtime. We know that. But we want to know is how far the difference we see is diverted from the right-hand side. Is that like can be explained just random variance, or there's something kind of significant that it's kind of unusual things happening compared to right-hand side? So how to test that difference? We know that there's a difference, but we want to know that that difference is big enough or just marginal difference. Okay, so how to test if the difference is significant or not? So there's 3 steps. First, calculate the expected values when assuming that there is no relationship between attrition and overtime. Basically, this is like a right-hand side chart. You remember like it's a kind of flat and an equal ratio chart. We want to know like where the expected values of like value. I'm going to go into more detail. And calculate the difference as a single metric, meaning this is what we wanted to do. It's like a left-hand side chart, right-hand side chart, and then that there's a difference there. So we want to understand, we want to actually sort of like a compute or like a calculate that difference. And then third, this is where the probability distribution comes in, because we know there's a difference, but that difference is far enough or big enough or not enough. That kind of question, we can use the probability distribution. In this case, something called chi-square distribution. So let's look at from the first one here. So basically, like we want to calculate the difference between the actual and expected. In order to calculate the difference, we need to know what's the expected data, right? So how we can calculate the expected values. So this is what we got, actual data. Left-hand side is a count, right-hand side is a ratio. Okay, this is just an example here. I just kind of made up the numbers here. Okay. We've been so far looking at the ratio chart, like 100% bar chart. That is basically right-hand side. Okay, and let's say like, overtime 30%, not overtime 20% people left the company. But the left-hand side is the numbers, the actual numbers, 60 people in each who left the company. So now let's focus on the count. So we have this, and even this count side, let's focus on this overtime folks. Okay, these people who have left the company already. And then these are in total, we have 200 people because 140 plus 60 becomes 200. So now here's the question. Out of these 200 people, how many of those is supposed to be for not quit or quit? Okay, so right now we know that we have 140 people who didn't quit yet, 60 people who have quit, right? But if the attrition, which is quit or not quit, and overtime, which is overtime or not overtime, if there's no relationship, okay, meaning that like a flat equal amount of people, equal ratio chart, in the expected world, how many people are supposed to be in a non-quit and how many people are supposed to be in a quit cell? Okay, right now 140 and 60, but that numbers should be different in the expected world where there's no relationship between attrition and overtime. To do is pretty simple, actually. The way you do it, first, like you might get kind of like confused, but when you think about it, eventually I hope you can see what I see too. So first, we calculate how many people in total for not quit and how many people in total for quit. And both of them basically like 380 people and 120. Okay. And this 380 and 120, we don't care who's overtime or who's not overtime, in total for non-quit and a quit. And then we calculate the ratio, respectively, the 76% and 24%. Okay. So that says if attrition and overtime are not related, then the ratio for the overtime should be as 24% and 76%. Okay, so right now, the overtime column, we have 140 people and 60, but that's actual. But we want to calculate the expected one. And that number should be reflected based on this ratio, which is 76% and 24%. What that means, okay. So left-hand side is actual data. So we have 200 people for the overtime, and out of which 76% of people should be assigned to non-quit. 24% of people should be assigned to quit. That is the right-hand side. Then you recalculate, then you get 152 people for non-quit, you get 48 people for quit. All I did is like a multiply 200 by 0.76 or 76% to get 152. And then like I basically multiply 200 by 24% to get 48. And that is the numbers that we expect if there's no relationship between the attrition and overtime. We can do the same thing, same calculation, where you apply 76%, 24%, this ratio against the total number of the not overtime, which is 300 people. Then we can get 228 and 72 respectively. And what this means is this. Look at the right-hand side chart. This chart is basically 100% bar chart, right? And left-hand side bar is overtime. Right-hand side bar is not overtime. And then the numbers are different, like 152, 48, and all that. But the important thing, the ratio is equal, okay? So the people who have left is in both sides, 24%. People who haven't left is 76%. And when you look at chart like this, oh, obviously there's no relationship. Yes, that's what we wanted to get. This is the expected one. If there's no relationship between these two variables, this is the kind of chart we should have expected. And then now we know the number of the people in each cell, okay? And once we have these numbers, then we have the actual data and expected data, or actual numbers and the expected numbers, okay? And once we get here, then how far is the difference in the actual data diverted from the expected data? What's the difference between these two? So the second step, to calculate the difference as a single metric. This is, by the way, the chi-square value. So we have the left-hand side actual and then expected data on the right-hand side. And we want to calculate the difference. How are we going to calculate that difference? Again, this is also pretty simple when you think about it. Each cell, in this case, let's say like overtime and then not quit people. Actual data, we have 140, but we have 152 as expected values. Then all we need to do is just minus it, subtract. What's the difference? Here is minus 12, right? And then we do this calculation. We basically do this, calculate the difference for each cell. So now next one is a no overtime and a no quit. Next one is overtime and a quit. The last one is a no overtime and a quit. And we get somehow the same kind of number, minus 12, 12, 12, minus 12. And then we want to combine these. We want to add them up to say, hey, these are the difference. The problem is this. Problem is that when you calculate, when you add them up, it becomes 0. And this most theoretically happen all the time because the expected is sort of like kind of a mean, is a kind of between value. So when you calculate some cells is bigger, some cells are smaller than expected. So therefore, like you tend to have this like 0 values. And we don't want to have that because 0 means 0, no difference, but there is a difference. So like, that's kind of weird. There's a difference between actual and expected, right? So what we do is, one way is basically like, get rid of the minus and assume that as a plus, which is absolute numbers. But in this case, we square, and that's where the chi-square, the square comes from. We square, then definitely like any like minus or negative number becomes positive. So in this case, like square of minus 12 and a square of 12 and a square of 12, square of minus 12, like add them up and then becomes 576. It's a huge number. And then but here is one problem, because now we know the 12 is a difference in each cell. But when you look at the red squared area, which is the overtime and the quit people, we have like only 60 people there, right? But expected is only 48. Either way, it's kind of smaller than other cell. Look at the blue squared cell. We have 240 in actual and 228 in expected. So should we treat this 12 as the same way, or should we treat them different, because 12 against expected number 48 is pretty big. It's almost like a 25% difference. But 12 against 228 or even 240, either way, is kind of 10%, not even 10%, maybe like 5% difference, right? So we shouldn't treat them as equal. We should just give the weights based on the number of people there. Okay. So therefore, we use the expected values and then divide for each squared values. So that's left hand at the bottom left hand side. It says 144 divided by 152. That 152 comes from the expected values of overtime and not quit. And do the same thing for each cell. Okay, and then basically like we give this sort of like a way, or like basically we want to express the difference in a percentage. Okay. And then like we calculate that, and then finally add these numbers up. And in this case, it becomes 6.579. Okay, so this is the chi-square value. So now the chi-square value is basically, it's a metric that measures the gap between the actual data and expected data, like this, okay? So left-hand side, we know that there's a difference, and the right-hand side, there's no difference, and how much of the gap between these two. And we calculated that as a chi-square value. So then the last step is that use a probability distribution. This is a chi-square distribution, by the way. That such difference would follow when assuming there's no relationship, and decide if a given difference is significant. So what that means. So far what we did is like overtime left-hand side and not overtime. And then we calculated that based on like the difference between of attrition rate. Right, and then we got this chi-square value. Okay, but this is the very common thing we do in hypothesis testing. Even if we sample from the same population, meaning same kind of people. Okay, so right now, so far, like we got people from like a different population, a different group, right? It's like one is over time, the other one not over time. But if we take the same people, let's make it simplify. We have the overtime people, all the people that work overtime, and then we take samples, right? Like let's say like 100 people sample and another 100 people, then we calculate the attrition rate. And it would be different because we just randomly choose the people, and then data varies in this real world. So there's always slightly difference. Okay. And if there's a difference, then we calculate the difference between the actual data and expected data. Expected, there's always no difference, but we should have some difference, even it comes from the same group. Okay. So then we calculate the chi-square value. It could be, who knows, 6.5, or I'm sure like it's going to be much smaller numbers. But, for the sake of simplicity, like it could be 6.5, or it could be 5.9. And if we take another sample, let's say like the population is the group in total is like 2,000, 20,000, whatever, and then we take 100 each, and then calculate the chi-square value, and it could be 5.9. The more we do, like the data varies, right? So it's always slightly different. But that difference usually, not usually, it's supposedly follow a distribution, and that's the chi-square distribution. The chi-square values would follow. Okay, if we assume there's no difference, between these two groups. And this is the probability distribution, and then we can actually use it to test or evaluate whatever the chi-square value we get from the actual data, the data in our hand. This chi-square distribution is a little tricky because the shape of that distribution varies depending on the degree of freedom. And the degree of freedom is always a kind of tricky concept, but this particular case is like when we're talking about the categorical variables, it's actually simple. what is the degree of freedom? So when in this case, we have the overtime and attrition, right? And both of them have two unique values each. And in that case, basically, when you know the one of the two unique values, you already know the others. So there is all basically the sort of like you can decide freely which value could be is only one for overtime, and the other one like the attrition too. Once you know one, you already know the others, right? So there's only one sort of like free to choose the value. So therefore, it's always for the categorical variable case that in order to calculate the degree of freedom is number of unique values minus one. And then in this case, 2 minus 1 multiplied 2 minus 1 equal 1. What if like when you have more categorical values or more unique values? In this case, we have 4 unique values against 3 unique values. Do the same thing. 4 minus 1, I think that arrow is kind of pointing a slightly different place. It should be something like this, right? So this one go here. And then 3 should be going here. All right. So this case, 3 minus 1 multiplied 4 minus 1 equals 6. So this is basically 6 combinations that we can choose the value in a free way, free way. Because other than that, like basically you know the values. For example, like you know the 3 values out of this like region, then you already know the last the remaining. So you calculate the degree of freedom, then you can choose which shape of chi-square distribution. You're not going to choose it when you do the testing. This is all sort of like behind the scene thing. But in this particular case, the degree of freedom is being 1. So the chi-square distribution shape looks something like this. Then we already calculated the chi-square value with our actual employee data, which is 6.5. And then like we see like, hey, where the 6.5 is located on this distribution. Then we want to see like a probability of getting this value on this distribution. And if it's a low probability, then that's kind of weird, but it's high probability, then, this can happen and it's sort of like randomly or often. Okay, so what that means. So you remember that framework? So we wanted to test the hypothesis or the sort of conclusion built on the hypothesis in the real world, right? So let's do the test. In exploratory, we can do chi-square test. I'm going to just use the exploratory quickly here. So we have this summary view. I'm going to go to the analytics view. Okay. And then here, under the analytics type, there's a statistical test. And then under that, there's a chi-square test. And then we want to select target variable attrition and explanatory variable, where's the overtime here. Okay, so this is overtime and attrition. And this sort of like order actually doesn't really matter if you flip. Let's say like you have the overtime for the target and the attrition for the exploratory, then you're going to get the same result because this is just a combination between the two categorical variables. But anyway, so then that's it, and you just run it. Okay, and basically by using target and explanatory value, what you're really doing is sort of like creating this pivot table, right? Think of it in Excel. And then you overtime and attrition, and then calculate this like a percentage. But that's not really the point. But we know the difference. Like for example, when you go to the ratio, so we know the difference. Okay, this is like overtime. Yes, people have more, percentage the employee who left. This looks like a huge difference, but we want to test if this difference is significant or not. And then the result is here. And then the two things you want to focus here is one is the chi-square value. That's the one I was talking about. And then what's the probability of getting these chi-square values based on the chi-square distribution, which is under the probability distribution. You can see this is the chi-square distribution. And then that chi-square values, which is huge, is like 89. And then that's actually comes around here. And then now the question is, what's the probability of getting this value? And that is here, p-value. And p-value says 3.86 blah, blah, blah. So that is that like 386%? Is actually no. Here, like it says E minus 21. And that's a kind of weird symbol if you're not familiar with it. That's called some exponential notation. So when you have the huge numbers, I mean large numbers, it's usually like it's a trillions and then gajillions or whatever that huge number, or the small number 0.0000, very close to the zero, but it's like a lot of like small digits numbers. Then there's not much space to lay out all the numbers. So we use the E notation or exponential notation, or sometimes we call it scientific notation, or whatever that is. So when you see E minus something, in let's say like E minus 5, that means 10 minus 5. I forgot how to say in English. This minus 5. So, power minus 5, power minus 5. So that means in a simple word, it's like you lay out the 0 5 times. So 0.0000 and then 1, 2, 3, 4. Okay. And if it's E plus, then 10 power 5. So it's opposite, right? So like when you have 1.234, then you want to multiply 1 million. Okay. Sorry, like 10 million, no, not 1 million, like 100,000. Okay. So having said that, like when we have the 3.86 whatever, and then like E minus 21, that means we're gonna lay out the 0 21 times, okay, 0.0000. And then eventually, like after that, 0, that's 386. So what this means is very close to 0. It's very, small numbers, right? Okay, so that's that p-value. So p-value is actually here, right-hand side. We got the chi-square value. And what is the chance of the getting this chi-square value? Following, like if we accept the null hypothesis, that means we, this not over time and not over time, there's no difference between them. Based on the assumption, we can draw this kind of probability distribution, chi-square distribution. But we got this chi-square value from this data. And then what is the chance of getting the value like this? It's precisely getting this particular value or larger values. And what is the chance of that? And that's basically the area under the line after this, green dotted line to the right side. So that is almost like a 0%, 0.0000, that crazy, like small numbers we saw. Okay, so almost like let's say like it's almost like 0%, right? And that's where we are now. And the last one is how we can actually make decisions based on this p-value. Okay, so what is your threshold line? I mean, threshold line is kind of the same thing, but what is your threshold between hardly happen or rarely happen and can happen, often happen? Okay, so in the hypothesis test, we use something called significant level. We decide, usually before you do this testing, you define what is the line, like threshold. And typically like 5%, 1%, 0.1%, or maybe some other, area, like you might have different numbers. It's just that, there's no objective logic behind this, but like we use some, we pick some numbers. And then typically like 5% is often used. That means if something's happening less than 5%, it's very rare. If something's happening like, greater than 5%, it's like a 10%, 20%, that's like, we can assume like that can happen. Having said that, let's say like weather forecaster people says like, hey, there's a less 5%, let's say like 3% chance of raining. That means it's not going to rain. It's if it rains, that means the weather forecaster is something wrong. The machine or whatever the logic they use is something wrong. It shouldn't happen. If it's a 10% chance of raining and it rains, and we can still assume like, oh, that can happen. So that's the kind of threshold we are talking about here. So let's say like we use 5%, then any p-value greater than 5% is, like I said, like the 10% chance of raining and rain. We don't go to the weather forecast people and like, angrily like knock the door and then break the machine or something like that. That's like, hey, that can happen, right? So therefore we accept, whatever the hypothesis, in this case, null hypothesis. But if it's less than 5%, let's say like 1%, in this particular case, 0%, then it shouldn't happen if the null hypothesis is correct. But shouldn't happen, right? So, but it's happening in the real world. So it's not consistent. So we can reject the null hypothesis. So what that means here, the right-hand side bottom, I mean, before that, left-hand side top, that's a null hypothesis, okay? That's a falsifiable hypothesis. There is no relationship between attrition and overtime. We start from there, but then therefore we could use the chi-square distribution, okay? But the chi-square value we got was like 89.04 or something like that. And then a chance of getting this value would be like almost 0% if we assume the null hypothesis. But it's happening, it's like not 0%, it's happening. So therefore, we can reject the null hypothesis, something like when, where we started with something wrong. So because the world of theory left-hand side and the world of reality and right-hand side are not consistent. So we reject the null hypothesis. And what that means, if we reject the null hypothesis, that means the opposite, right? So that means there's a relationship between attrition and overtime. That sort of wording around this, depends on who you ask, might be different, but at the end of the day, that's what we are heading to. We can say like, hey, we can't say there's no relationship or there's no little evidence to, various ways of describing this, but at the end of the day, basically what we are getting to is there is a relationship between attrition and overtime, like we already kind of know by looking at the chart. But now we actually sort of like confirming that by using this chi-square test. And what that really means is like, hey, data values. So even though like when you looking at the chart, there's a difference, that doesn't mean that's the significant difference. And then what if like, like the people who work overtime is only like 5 people. And then when you have like, people who don't work overtime was like 1,000 people, then can we really compare those two groups? And then we can conclude, and probably not. So this type of the testing consider taking into account of those type of number of the people and or data size or sample size. So so at this stage, basically, like we have sort of like tested it in more sort of like I'm not sure it's the right way to use this word, but like robust, or like it's more we are more carefully tested by using statistical technique. Okay, if the p-value this time was almost 0, but what happened if it's 25% or 15% or bigger than 5%? What should we do? Well, in that case, hey, that 25% or 10%, whatever, that's like, hey, that can happen, right? We decided that if we use a 5% of the threshold, it's bigger than 5%, that means it's like same thing, the 10% or 90% is same category in this case. So that can happen even if the null hypothesis is correct, or like assuming null hypothesis is correct. So therefore, so far, so good. I mean, the null hypothesis is still working. There's nothing to reject the null hypothesis at this point. What we expect based on the null hypothesis is happening in the real world. So therefore, we don't have to reject it. We can accept it and go on with our life. That means there is no relationship between attrition and overtime. That's a null hypothesis. We're going to go along with it. Okay. So that's really the chi-square test. I like to summarize what we have talked about today. There's a bunch of different way to do the hypothesis testing based on that data type. In this particular case, we talked about categorical variables. By the way, the logical data type is also considered as part of categorical. It's just a very special case of like having the value either true or false. So in that case, we use a chi-square test. We use the example of attrition over time. We wanted to test, there's a relationship between these two. And the chi-square test is to test if a given pair of two categorical variables are independent or not, or related or not. Okay. Then basically left-hand side is what we see in the data, but expected data is that same ratio. So basically we wanted to evaluate the difference we see is how much diverted from the expected data. Then there's a way to calculate that difference as a single metric is called chi-square value. And once we get that value, then we use a chi-square distribution, which is a probability distribution. Then we can calculate the probability of getting the chi-square value. And based on that p-value, we decide if that difference is significant or not significant. If the p-value is closer to zero or small enough, then we can reject the null hypothesis because something shouldn't happen is happening in the real world. So the world of theory and the world of reality is not consistent, not matching. Therefore, we reject the theory or the null hypothesis in this case. Then we go to the opposite conclusion, which is there is a relationship between attrition and over time. By the way, one thing I forgot and I was planning to do and I forgot to do it is that just quick and then here in the exploratory, like you can actually go to the summary view, right? And then this time, like we did only particularly like investigate the relationship between attrition and over time. Right? What if in the more like EDA scenario, like, hey, I want to see like business travel has anything to do with attrition. I want to see department has anything to do with attrition. How about like education? How about gender, right? And you can run those things one by one under the analytics view, or you can actually go to the correlate, and if the target variable is logical, then in this particular case, it's only logical. If it's character, you can't do it. But if it's logical, then you can use this correlation mode under the summary view, and then run all the variables in once. So what that means, I'm going to select attrition here. And then this point, it tests against all the variables. So for example, here, like a business test, and you see here in a p-value and chi-square test, and then it says less than 0.0001. That means close to 0. So this one is significant. And then like you see here is that, okay, like, it depends on the business travel, attrition rate is different. So it's sort of like you don't even have to run the test. You already kind of know, even including the confidence interval, but you can see that test right away, test result right away. How about a department? It's 0.0045. So it's like this is like 0.4%. So it's small enough. Okay, so there's some difference there. You can actually sort by the p-value. And then let's say here, gender, this is like a p-value is pretty big, 0.25. That means 25%. So that means the gender and attrition, the null hypothesis, there's no relationship. And we can't reject the null hypothesis. So therefore, like we're going to go with there's no relationship. You can sort by the smaller p-value, so ascending. Then you can see, okay, these are the variables that have a relationship with attrition. When you go down, then the p-value started becoming bigger around here. Then, okay, these are the ones that doesn't have the relationship against attrition. Okay, and then what if like my variable is, let's say something like, let's say a gender or something, but I want to see the relationship against gender. These are just a two. Then you can actually create the logical data based on this gender values. That like I have done like how to create logical variable seminar before. So I recommend you to take a look at that one as well. Okay, so I just wanted to share with you guys how you can run that chi-square test with all the variables at once. Okay, so time has already passed, so like I'm gonna close at this point. If you have any question, the feedback, please reach out to me at exploratory.io. Otherwise, I'm gonna hopefully I'm gonna see you guys next week with a different seminar. Okay, thank you so much for joining, and hope you are going to have the great rest of the day. All right, bye.